Welcome to this Chapter 6 video where I discuss xv6 system calls and where they're located within the source code that you're going to be working with. So let's go ahead and begin. The first thing we're going to do is we're going to talk about, we'll start by showing you a list of the files. There are 6 files that are critical to the system calls that we're working with. You will have to modify these 4 files here. These 4 files are necessary to define the system calls. And then there are these 2 files here where you'll put the actual system call function handler code. We'll go through each one of these files one at a time. Let's start with user.h. This is in the user subdirectory. User.h is a header file that contains the system call function declarations. These system call function declarations give you an idea of what the system call should look like. So let's go to our terminal and we'll take a look at user.h. In user.h has 2 sections to it. The first section is the one we're going to talk about. It's where the actual system calls are located, or where the actual system call declarations are located. There's also a declaration section for library functions. Feel free to use these functions in your user space program. So let's talk about these system calls. The system call declarations are not actually code, but more just what you should use when you call it and what to expect in return. All of these functions seem to return an integer, except for this sbreak, which we will talk about when we get to the memory section. The integer is fairly common return for the system call, but the parameters that are used to call the system call tend to be quite varied. For example, the fork system call doesn't take any parameters, and this is typical for the fork. Exit takes an integer parameter. This identifies the exit status for the process. Wait takes an integer pointer, which allows the kernel to insert a integer value into a variable that represents the exit status of the return child. Write takes 3 parameters, an integer, a memory pointer, and another integer. So these declarations are used by your user space program to make sure that you're using the right parameters or the right parameter types when you make a system call. We're going to follow, as we go along, the path of the wait system call and the write system call. So let's keep those in mind as we go along. So the next file that we need to look at here is the usys.pl. Again, it is in the user directory. While user.h header file is used directly by your user space code, usys.pl is used indirectly. Usys.pl is a code generator. It actually writes code for you. Isn't that handy? What it's writing is it's writing system call function stubs. All those functions you saw earlier, there has to be a function somewhere in your user space. Well, what's happening here is these functions are being generated by usys.pl so that the linker can find them and link your user program to something that works. But what that particular piece of code is looks a little strange. So we're going to go back to the terminal now. Let's go ahead and exit out of user.h. And let's go ahead and edit usys.pl. Now, usys.pl can be broken into 2 parts. Let's look at this entry part first. You'll notice that there's an entry for each one of the system calls. Here is entry wait, one of the calls that we're following. Here is entry write, which is another one of them. You'll notice they're not necessarily in order. They don't need to be. That's okay. what we want to see is, what is this entry that is being called? Well, this is a Perl function that is being defined up here. When this Perl script runs, each one of these entries will call the entry function with the name of the system call. That name is being used to create some assembly code. So you are actually building programs that are user space programs that have assembly code written into them. You don't have to worry about what this assembly code does. The two most important parts of this is this line 13, where we're loading into register 7 a value SYS underscore, and then the name that was passed in. So if we follow through with wait, there's going to be an assembly language line, li a7, comma, sys underscore wait, as well as sys underscore write and all the others. Then it calls, then the second instruction, machine instruction here, is ecall. This ecall is actually what causes your user space program to switch to the kernel mode. Now, you'll notice here that we're just putting in a number, and we'll see those numbers shortly. The ecall does not have a specific memory pointer that you can use, but the kernel has set this beforehand. It is called the trap handler address. The trap handler address is programmed into the CPU, but cannot be changed by user programs. So user programs can only call ecall. Once ecall has been executed, it's like it's doing a jump, an instruction jump, somewhere inside the kernel, and switching to kernel mode all in one instruction. In effect, your user program basically loses control of the CPU for a period of time. So if we go back to our list, those are the two user space source code files that you need to be concerned with. User.h, where you need to add system call function declarations, and usys.pl, where you will add an entry call for any new system calls you create. So let's take a look at the kernel space source. We're going to start with syscall.h. Now, if we look at syscall.h, so quit out of usys.pl, vim kernel syscall.h. This is a very simple header file. It has a bunch of pound defines. These are basically creating what are called macros. These little macros are just simply representations of the value that follow it. So if we look at sysfork, sysfork will be replaced with the number 1 every time it's found. Syswait, the one we're finding, will be replaced with the number 3. Syswrite, and you'll see syswrite way down here, it's number 16. Again, it's not ordered the same order as the user space. Syswrite is 16. Note that all the numbers increment and are unique. There is no other number 1 system call. There is no other number 16 system call. These are all unique with relation to each other. Also note that they all start with capital SYS underscore. This was, if you remember back in the usys.pl, what was being used to generate that register load. The LI into register A7 was using SYS underscore and the name. Well, here is where that name comes in. In effect, the code generator is taking these numbers and loading register A7 with this number, and then running the ecall assembly instruction. So let's take a look at the next file after syscall.h. So after syscall.h, we're going to look at syscall.c. Syscall.c defines a very important structure for this operation. It's called the system call handler vector. A vector is basically just an array of pointers to functions. And so this is an array of function pointers that will be used by the kernel to find the correct function based on the system call number. So let's take a look at syscall.c. We'll go ahead and quit out. We'll call edit syscall.c. Now there is quite a few functions here. We'll skip over those. We come down here towards the bottom of the file. So for my example here, it starts at line 86. It should be the same, but it could be different. Here is the system calls handler vector. It is an array, so we can see that it's being declared as an array. But what is an array of? Well, oddly enough, it's an array of functions. And the way you define a type for a function is you define the function's return type, and then in parentheses you specify asterisk, and then the variable name. And in this case, we're using the array element to declare that it's an array. Then you end that particular parentheses and start a second set of parentheses that shows the parameters. In this case, all the system call handler functions will take a void type. Now this may seem very odd because if you remember back in user.age, that system calls came with lots of different parameter types, such as weight. The weight function required a pointer to an integer, and write required a integer, a memory pointer, and an integer, so 3 parameters. While this is true for what you're doing in the user space, the actual in-kernel function, system call handler functions, should always take no parameters and should always return this type, the uint64. So here's the vector from this point all the way up to this point. This is the system call handler vector. Each system call has the declaration written there, as well as where in the vector it's going to go. And you'll see that each position should be filled within the vector. But where is this particular function name coming from? Well, within the particular syscall.c file, we also have declarations. These are the function declarations for your system call handlers. Each system call handler must have a declaration before it's used in the definition for syscalls. So when you create a system call, you'll go ahead and add something here. You'll see there is a function declaration for weight, and you'll see there's a function declaration for write. So all the handler declarations can be found in this section of code before it is used within syscalls. So let's take a look at what's next. So we've talked about these 4 files. These 4 files are critical for creating a system call. These 2 files here are not necessarily critical, but they're important. sysproc.c is where the handlers are for process-related system calls. And sysfile.c is the source code where you can find the system call functions for file-related system calls. And if we think closely about the 2 that we're following, the wait system call should be in sysproc.c. And the write system call, which writes to files, should be in sysfile.c. So let's go back to our source code. What we're looking for is we're looking for functions that have syswrite in their name and syswait. These are the function names that must exist inside the kernel for all this to work. Now I'm pretty sure I know where those are. Those are in sysproc and sysfile. But let's say I didn't know where those two calls were. Well, I'm going to go ahead and grep for, I'm going to do it recursively, for syswait, and I'm going to search the kernel subdirectory for the syswait function call. Now here is the two lines that are in the syscalls.c, the declaration for syswait and the usage of that declaration within the system call handler vector. Here is where the actual function for sys_wait can be found. It is, as I stated, in kernel/sysproc. Now, it wasn't guaranteed that that's where that function call was, which is why I called grep. I called grep to make sure I knew where that was. But now I can go ahead and edit sysproc.c. Now I'm going to go ahead and search using vi search for syswait to get to the syswait function. And here it is in line 33. Line 33 shows, here's my syswait. Again, syswait must take no parameters and must return a uint64 variable type, a 64-bit integer. Syswait does some very important functions, and you're going to see this a lot. Remember that the actual user space wait system call takes one parameter, an integer pointer. Well, an integer pointer is a memory address. And so the first thing syswait does is it asks the operating system kernel for that memory address. It says, please give to me the memory address for the that was passed when the user space program called the wait function. This is where the parameters come in to the system call handlers. System call handlers gets all their parameters by calling one of these arg functions. Here it's calling arg address because an integer pointer is coming in. This exit function call is calling arg int because an integer is being passed into exit. We'll see what our syswrite does here shortly because it takes 3 parameters. In any case, all syswait does is it gets this pointer, it makes sure that it's a valid pointer. If it's not, if that pointer doesn't validate properly, it will return a -1, which is an error state. If it's successful though, it'll call the wait function inside the kernel. Let's go ahead and see if we can find this wait function. I'm going to go ahead and quit out of here. Grep wait. And this is actually going to return back a lot of possible answers. So there's wait all over the place. Most of these are comments. We probably can skip over the comments one way or the other. Here's where syswait is defined in syscalls.age. That's fine. More comments. Here's something called wait lock. That's not what we're looking for. Just keep going, keep going, keep going. There's wait lock. Here in proc.c is the wait function. So I'm going to go ahead and edit kernel proc.c. I'm going to search for wait. And it's going to take me a couple times to get there. There it is. So here is the wait function. Wait function takes an address and performs whatever operation it needs to. Clearly, this is a fairly complicated function that the kernel has here. This kind of operation is taken care of inside the kernel in their specific in their specific source code. So you'll generally have very small system call handler functions that call much more complicated system functions or kernel functions to get the actual work done. Let's look for the write. So I'm going to the write system call. So if you remember, that one is called sys_write. Now the sys_write function, we see here, there is the syscall.c where it's declared, syscall.c where it's used in the vector. But here is sysfile.c where syswrite has been defined. So I'm going to go ahead and edit kernel sysfile.c. Let's go ahead and search for syswrite. And here on line 82 is syswrite. Again, syswrite takes no parameters, which is what system call handlers must do. Remember, you do not send parameters into these functions through the function parameter list. The way we do this is we use these arg functions. Remember that the write system call has three parameters. It has an integer for the file descriptor, has the integer for the size, and it has an address for the pointer. And here are the three functions. There's argfd, which gets a file descriptor. Here's argint, which gets the integer parameter. And here's argaddress, which gets the memory pointer. How does it know which one it's getting? Well, that's what the first value of these arg functions represent. The 0 here says that the first parameter, remember, we're dealing with C and 0 indexed parameters. The first parameter of the system call is a file descriptor, and thus it will read it into that file descriptor variable. The second parameter, or index number 1, is an address, and so that address will come from parameter index 1 and be stored in this p variable, which is a uint64. It's going to be used as a pointer. And then finally, the third, or index number 2, is an integer. And so we're storing into the n variable, an integer variable. We're storing into that variable whatever the integer parameter was. And then, and if any of those parameters were not successful, so these functions will return 0 or better if it was successful. But if there was an error, these functions will return less than 0 if there's an error. So if any one of these returns an error, then the system call handler returns a -1, which is an error state for the system call. But if there wasn't an error reading any of those values, then the file write function is called with those three parameters. Again, system call handlers are usually small programs that get the parameters and then call something more extensive to get the work done. So let's create our own system call. I'm going to create a very simple system call. All it's going to do is take an integer and then multiply it by 2. And I'm going to call it something very simple. Let's go ahead and first edit user.h, and I'm going to create a system call down here, and I'm going to call this ×2. And it's going to take an integer. So ×2, all it's going to do is multiply a number by 2. Nothing more, nothing less. And so I declare my system call function here in user.h. Now I need to edit usys in the user directory, usys.pl. And I need to add an entry. So down here at the bottom, I'm going to add entry ×2, close quote. That's it. This will generate the system call stub in order to call this, my ×2. Now, of course, ×2 is now going to need this sys_2 system call number to work properly. Where do we edit that? We edit kernel/syscall.h. In syscall.h, I'm going to go ahead and do a #define sys, all caps sys, ×2. And then I'm going to give it a system call number, which is the next sequential number in the list. So the last one previously was 21. My system call number is 22. System call numbers will be different if you have more or fewer system calls in the system. So it may be that you create a system call number 23 or 24, depending on what the last value is. I'm going to go ahead and save this syscall.h. And now I'm going to edit syscall.c. I'll go to the bottom of the file. Now, syscall.c requires me to make two changes here. The first thing I want to do is I want to create a system call declaration, system call handler declaration. It is always an extern type. uint64 is its return, and I want to call it sys times 2. Notice that I used lowercase sys here, and its return, or its parameters, always void, always void. So that's my declaration for my new system call function. It's real simple. Just simply follow the pattern that was used in the previous system call declarations. Now that I have my system call declaration and I have my system call number, I can add a new line to my syscalls handler vector. And I'm going to open with a square bracket, sys times 2, close bracket, sys underscore times 2. And I put a comma at the end of that so that it's available for the next function, next entry that comes along. So again, I've added a connection between my system call number and my system call handler. So where do I add this function? That's a good question. It doesn't have anything to do with processes or files, but since proc is probably where we're going to spend a lot of time, let's go ahead and add it to sysproc.c. So inside sysproc.c, I need to actually declare a function, or define a function for this. And so let's go ahead and just simply copy the pattern that we see for syskill. Syskill takes an integer and will return a result. So I'm going to create a function right after syskill. It doesn't matter positionally where these functions are. It's going to return a type of uint64, and its name is sys times 2, and of course takes the parameter of void. Now, I need to somehow get the value that I'm going to multiply. So I'm going to declare a variable called value. Now I'm going to get the number that was passed by the user space program into my val variable. And I'm going to do that with the argint. I'm going to test argint's return to make sure that it came back correct. Now the first parameter for argint, I only have one parameter here, and that is 0. And then I go ahead and specify that I want it to put the number into val. I'm sending a reference to val because that's the only way I can have something write data into that. I'm going to go ahead and check to make sure the return is not less than 0. If it is, I'm going to go ahead and have it return an error. If it was successful, if it successfully got my integer, I'm going to go ahead and return value times 2. This multiplies the value and returns it back to the caller. Now the whole return process is covered in the system call handler source code for the xv6 operating system. And we'll show that in a later video. But at this point, my system call is written. If we go back to our files used in system calls, let's take a look. I modified user.h and added the times 2, which takes an integer parameter. I added times 2 to usyspl as an entry. I created number 22 for my new system call in syscall.h. I then added a declaration for sys times 2, and then added an entry to the system call handler vector. Then I edited sysproc.c and created a function that multiplied numbers by 2 and returned the result. We need to write a user space program to take advantage of this. So let's go ahead and write ourselves a real simple user space program to make sure that this works. So I'm going to write and quit. Let's go ahead and create user/test times 2.c. So test times 2 is the program I'm going to create. it needs to include user.h, and I'm also going to include kernel types. And actually, I've got that in the wrong order. I've got to put kernel types first. And include kernel types h, and then user. And I'm going to create my main function, int argc char pointer argv parenthesis. There we go. And of course, I have to exit to properly terminate my program. So I'm going to create a very simple program here. All it's going to do is create a variable, int n, or we'll actually name it val, equals 42. Then I'm going to go ahead and declare int result is equal to times 2 of value. Remember, times 2 is my system call function that's declared in user.h. Now I can go ahead and printf the number %d times 2 is %d. And we'll go ahead and pass it val and result. So very simple function. I'm creating a variable with a number. I'm sending that number into my system call and taking the result and storing it into a result variable. Then I'm printing out the results. Now for this to work, I have to edit the base make file, go down to user progs, and add my new times 2 function. So I'm going to go ahead and put times 2 in here. Oh, it's test times 2. This is the program I've created. So I created the program source code file test times 2.c. I'm adding it here to uprogs so that it can build my test program and I can run it in xv6. Let's go ahead and save that. I'm going to make sure that everything's clean by typing make clean and then make qemu. The kernel is now booting and everything is started up. If I type ls, we can see that I now have my test times 2 program inside the system. If I type test times 2 and press enter, it now says the number 42, which was the value that I assigned to the variable and passed into the system call. So 42 times 2 is 84. And that's correct. My system call worked. If this were a good test program, it would actually validate the value 84 and make sure that it was correct. If it was, it would say success. If it wasn't, it would say failure. So what we've seen today is how to create what files are necessary for the system calls and how to create our own system call within the xv6 operating system. This concludes the Chapter 6 video where we talk about system calls in the xv6 operating system.